So we have a loop which has a current inside of it. It has two semicircles, one bigger semicircle, one smaller semicircle. We're given the individual radiuses or radii of each of those semicircles, A and B. And the current is 7 amperes going like this, as we can already see. And we're trying to find the field strength at the center of the semicircles, which is at this point down here, the field strength on this blue point. So first things first, I'll break this massive semicircle into 4 pieces. This semicircle is going to be piece 1. This horizontal wire is piece 2. This semicircle, the smaller one, is going to be piece 3. And this last wire is also going to be, it's going to be piece 4. Now I'm going to use the right hand rule, and I'm going to draw the magnetic fields from piece 1 and piece 3 on this point here in this area. So for piece 1 I'll use this color, and for piece 3 I'll use this color. I think it's better to do it this way. Yeah, so this color for piece 1, this color for piece 3. I'll start with segment piece 1. My thumb is pointing left. Let's assume that your tablet is flat on the table and you're looking down on it. Your thumb is going to point towards the left, like parallel to the floor or parallel to your tablet. And initially you're going to curve your fingers. So at the top of the wire, we're going to have the magnetic field going inside. But we don't care about the top of the wire up here. We care about the bottom of the wire here, because we want to look at what the semicircle does all the way down here at the point. And this point is at the bottom of that larger semicircle. So hence, initially, the magnetic field at the top of the wire is pointing into the screen, but that's not important. It's what's below down here. What we figure out is that the magnetic field down here below that semicircle is pointing towards us, or towards the roof, straight up to the roof, assuming that your tablet is flat on the table. And so if I go all the way down here, we're going to have the same thing. Imagine you have this bigger semicircle and we ignore the rest of the shape for a second, and our point is here. The magnetic field below the semicircle in this entire region is pointing out towards you anywhere here. So it's going to be the same thing on the point. It's going to point out towards you, out of the page or out of the tablet, straight up into the roof, assuming that your tablet is flat on the table. So that's great. The magnetic field of the first piece 1, is pointing out of the page. Awesome. Now let's focus on piece 3. We use the right hand rule. Our thumb is going to point, I'm going to assume I'm standing here, so like horizontally on that smaller semicircle. My thumb is pointing towards the right, parallel to the floor or parallel to the tablet, again assuming that it's flat on the table. And then I'm going to curl my fingers. As I curl my fingers, initially the magnetic field will point out of the page towards the roof, assuming that my tablet is flat on the table. Initially, at least above the semicircle, this is what it's going to do. As I keep curling my fingers though, and I go below the semicircle into this region, the magnetic field by the smaller semicircle is going to point into the page or into the tablet that is flat on the table. So the magnetic field by this third piece is pointing into, this third segment is pointing into the tablet or into the table. or if you're on a laptop and your laptop is sort of parallel to the wall in front of you, then you're saying that the magnetic field vector of the third segment is pointing towards the wall, through your laptop screen towards the wall, and facing you, towards the wall facing you. Yeah. Okay, that's awesome. Now for these two segments, you have to realize something important. This point here is horizontal to both of those segments of wire, piece 2 and piece 3. When we're usually looking at a wire like this, we want to find the magnetic field here, so you're still at, like, a distance from the wire. But in this case, if we extend these wires like this and make them infinitesimally long, our point is right on both of these wires, both of these segments. And so what that tells us is that our angles, both of our angles, theta 1 and theta 2, are actually 0. So hence, that's why I didn't draw the magnetic field by these two segments, because they're not important. They don't contribute anything. If the point that we were looking at was like out here or something, then these two segments, segment 2 and segment 4, would actually give a magnetic field. But the fact that we're standing between these two wires anywhere here will always give us a magnetic field of 0 by this segment and by that segment. Basically, to show you more clearly, that angle is 0 and that angle is 0. When you do sine of theta, that gives us 0. So when you do 0 plus 0, it's equal to 0, and 0 times that expression there is going to give us a magnetic field of 0. That's all it is. Now that we have that down, so now I'll start with the first segment, the larger semicircle. I'll say B1. I'll use a smaller font. So B1 is equal to, it's in 4 pi times 10 to the power negative 7 Tesla meters per ampere, times the current, which is the same in everything, 7 amperes, divided by 2 times r. Now the radius of the larger circle is described by b, and b is, hold on, where is it? Yeah, there it is, 45 centimeters. I'll convert that to meters, so it's going to give us 0.45 meters. .45 meters. Awesome. Now, there we go. Now I multiply by something over 360 degrees. The maximum angle that a semicircle can form is always 180 degrees. Think of the unit circle, and a semicircle would be half of a unit circle, so that's 180 degrees. That's the maximum angle it can form. Now, if we weren't looking at a semicircle and we're looking at like a quarter of a circle, then the maximum angle it can form, if I draw the x and y axes, is like 90 degrees. So that's what we would use over here, if that was a quarter of a circle, but it's not in our case. Now we already know the direction as well, right, of our B1. It's always pointing out of the page, so in the positive k direction, positive k hat direction. And now I'll plug this into the calculator. And that's going to give me a value of positive 4.80, rounding things up here, 4.89 times 10 to the power minus 6. Tesla in the k-hat direction, the positive k-hat direction. Now I calculate the magnetic field by the smaller semicircle at this blue point. I'm going to be using the same formula, so I'm just going to copy paste it because that's literally what we're doing. The only thing that's going to change though is simply our radius down here, because it's everything else is going to be the same. So our radius is now A for the smaller semicircle, and A was 5 centimeters, which is 0.05 meters. 0.05 meters. I'll call that was B3. And remember that the magnetic field is pointing into the page. It's going to be negative k hat. That's the coordinate axes, by the way. So instead of positive k hat, we have negative k hat. So literally almost everything is the same, like the above equation, but only slight changes: the radius and the direction of the magnetic field. So I'll plug this into the calculator. It's definitely in the negative k-hat direction. That's going to give us negative 4.3. I'm going to round up, so 4.40 times 10 to the negative 5 Tesla in the k-hat direction, the negative k-hat direction. So that's negative 4.48 times 10 to the negative 5 in the k-hat direction. Now we want to find the field strength at the center of the semicircles, basically the net field strength, the net magnetic field at this point. So all we have to do is sort of add B1 to B3 to get that, which means basically our net magnetic field at the point is equal to, and I'll come back to blue now. Is going to be negative 3.91 times 10 to the negative 5 in the k-hat direction. So basically the net magnetic field is in the negative k-hat direction, sorry. And is that correct? Yeah, so it's into the page, so we're right there, and it's 3.91 times 10 to the negative 5, that's correct. The only reason I'm using a minus sign here is to tell us that's pointing into the page, into the negative k-hat direction. Here, since they've already told you that it's into the page, you don't need to worry about the showing the direction in unit vector notation. You just have to plug in the actual number, the value here. That's pretty much it for this problem. I hope this helps, and again, if you don't understand anything, always ask your teacher, or maybe look somewhere on YouTube. You might find some good channels there. Take care.